Charge Tape Revisited, and my name is Arianna Rahmathulla. The purpose of this lab was to find the amount of charge accumulated on a charged object, tape, where tape is modeled as a line of charges. We used Newton's second law and understanding of charges, interactions, and transfer, as well as Coulomb's law, to find the electric field and then force due to that field. And we also knew that the dq equals charge density times dl, where dq is a very small chunk of charge q, and dl is an infinitesimally small amount of length L. For our results, we found that the charge on tape 1 was manually calculated at 2.108 times 10 to the negative 8th coulombs and computed to be 2.261 times 10 to the negative 8th coulombs. The procedure was the same as lab 1, and our physics, our system was tape 1, surroundings was everything else. Newton's second law says sum of F equals ma, and we know that the two forces were the electric force, overall shown in white, and the gravitational force, shown in yellow. Coulomb's law is given here, and from Coulomb's law we can see that dE, or the infinitesimally small electric field vector, equals k dq over r squared, where dq is again an infinitesimally small amount of charge. Our data and constants were the same as lab 1, and we know from lab 1 that the net force is 0 and the electric force is equal to the gravitational force. So solving for the electric field, we know that dE, it says dE rod here, but that's just the dE of a line of charges, is given by k dq over r squared. Now our r, we know because we are finding the distance from tape 2 to a small charge along the length of tape 1. There is both a y component and an x component. So the y component is the distance between the tapes, and the x component is whatever horizontal distance that charge is offset from the middle of the tape. Now we know that dq equals charge density times dl, and charge density is just total charge q over total length L. Substituting that in, we get an expression for the dE of our tape, and we only care about the y component because the gravitational force is only in the y direction, so we need to set the y component of the electric force equal to gravitational force. So therefore, we only need to integrate the dE of our tape, the y component of that. So we integrate the y component from 0 to L over 2, so that gives us half the electric field overall, and then we can multiply that by 2. So I got an overall electric field y component to be this expression. I substituted in the constants that I showed you guys earlier, and then multiplied that by q again to get the electric force in the y direction, and set that equal to gravitational force and solved for charge. In my code, I assumed that the charges on the two tapes are equal and evenly distributed, so the charge density was constant. I treated the tapes like a line of charges, and I assumed that the net force was 0 and there was no air resistance. So in my code, I took my Q original, which was the overall charge that I calculated in lab 1, and I used that to find an initial electric force when I ran my code. And it was not equal to gravitational force, obviously. So to get my Q that I used in the actual computation, I multiplied it by an arbitrary constant, c, and I kept increasing c until I got to the point where the electric force equaled the gravitational force. It's 2.4236. But my Q calc here is what I calculated earlier. This is the electric field function to calculate the electric field. And then this for loop essentially finds the electric field for each of the very small dq charges along the length of tape 1. And in this model, there are 10 dq charges, and this for loop also calculates the electric force overall for each of those dq charges and sums them up. So visualizing, the red is tape 1, the blue is tape 2, the green is the dE along the length. The overall E force, the electric force, is the white arrow, and the overall gravitational force is the yellow arrow, and then we can see that the two forces are equal. What if I had modeled each of our tapes as a single point charge? Well, the charge would be 9.33 times 10 to the negative 9. However, it was 2.108 times 10 to the negative 8th, so the overall charge on the tape is greater in the line charge model than the point charge model, and that's because the line charge model treats the tape as a charge distribution, so it accounts for the electric field vectors for each infinitesimally small chunk of charge dq along the length of tape 1 and sums that, which is more accurate So some sources of error were not accounting for air resistance, measurement mistakes, and treating the system like a one-dimensional model while the tape was 3D. And obviously, our tape is still not a line charge like our model, and charge is not evenly distributed. So charge density is definitely not constant, and the tapes do not have the exact same charge, tape 1 and tape 2. So our charge was manually calculated to be 2.108 times 10 to the negative 8th coulombs and 2.261 times 10 to the negative 8th coulombs by computer, and we found the line charge model resulted in a higher amount of charge on the tape than the point charge model and was more accurate than the point charge model as well.